Yeah, Diwali, some people, we were
Yes.
getting some message due to this crackers something, and now the
Yes.
temperature also went down. I think, I don't know what is the
Mm. And
reason actually.
the reason I guess is absence of social distancing during Diwali. Lot of people going out
Yes,
and
not there are the several things that happen together actually.
yeah, yeah,
Diwali is one thing, then this Chhat Puja is also being held,
yes, yes,
then Durga Puja also held some
yeah,
the consecutively two, three occasions actually.
yes,
And then this election, the rallies were also held.
yeah, 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 all together.
There are so many things at a
Yeah,
time actually.
yes, true.
And okay, so let me start this session actually.
Yeah,
So, very good afternoon to everyone present here. So, I, Dr. Rajkumar Arya, Associate Professor in Department of Chemical Engineering, NIT Jalandhar, uh, welcomes you this for this session. That is the second session of day 4 on our online STC, Computational Methods for Engineers and Analysis, and conducted by Department of Chemical Engineering, NIT Jalandhar. The convener of the course is Dr. Anurag Kumar Tiwari, and patron and head of the department is Dr. Sangeeta Garg. So, a speaker for our this session is Professor Jalesh L Purohit, and who would talk on solution of nonlinear algebraic equations, ordinary differential equations, and brief about the partial differential equations. So, let me introduce Dr. Jalesh to all of you present here. We have amidst us Dr. Jalesh L Purohit, who is a professor in the Department of Chemical Engineering at Dharam Singh Desai University, Gujarat. Prior to joining uh, DD University, Dr. Purohit worked with several industries like Naveen Fluorine Industries in Surat, Narmada Chematur Petrochemicals the Limited, NC, NCPL Varuch, Gujarat, uh, Sabraznik Sarvajanik College of Engineering and Technology, Surat, Gujarat. On the educational fronts, Dr. Purohit completed his PhD from IIT Bombay, ME from DDIT Deemed University, and BE from Gujarat University. Dr. Purohit has one book chapter to his credit and 6 peer-reviewed journal publications. He has also 12 peer-reviewed international conference proceedings, 14 national proceedings to his credit. He is also a reviewer in national and international journals like Industrial Engineering and Chemistry Research, Chemical Engineering and Processing, Process Intensification, IFAC, Papers Online, among others. Dr. Purohit was awarded National Scholarship Scheme and Merits Certificate in SSC exam by the government of Gujarat in 1986. He also received the QIP fellowship from the MHRD India for higher studies, PhD from IITs, for the PhD for the period of 3 years, 2008 to 2011. He also got the Best Paper Award for the paper Observer-Based Nonlinear Predictive Control of Index 1 DAE Reactive Distillation System exhibiting multiplicities presented at RSS 2012 held at IIT Bombay. So with this short introduction, now I would like Professor Purohit to conduct the session. Over to you, sir.
Thank you very much, Professor Raj, for your kind for introducing me, kind introduction. Uh, I start now my presentation. Okay, let me present my screen. So is my screen visible?
Uh, uh, yes, yes, it's visible.
Okay. Okay. So since last 3 days, I'm also attending in between sometime. I was offline, but most of the talk I attended partially.
Yeah, yeah,
So yeah,
most of the tasks.
so it was started with regression, and there was a talk on numerical integration, differentiation, RSM, and data analytics, particularly applicable to closed loop PID performance while monitoring, interpolation, and molecular simulation, etc. So the most of this talk are either based on the industrial experience or the research experience. However, my talk will be more on basics of topic, that is numerical solution of algebraic equations and partial differential equations and ordinary differential equations, as suggested by the coordinator of this program. So, with this, I start my talk. Mm, okay, so let me switch off my camera. Okay, okay. So this is the outline of my talk. First, I will discuss about nonlinear algebraic equations and the solution techniques, that is open methods and closed methods. Then after this, I'll talk about ordinary differential equations, the solution of initial value problems and boundary value problems. And finally, I'll brief about partial differential equations. And in between, some demo programs on MATLAB I will also demonstrate. Most of the problems that I have included in this talk are very academic problems, not a research problem. So, when we carry out any mathematical modeling of, in particular, chemical processes or chemical systems, uh, we first try to use first principles, that is conservation laws, transport processes, and equilibrium conditions to arrive at mathematical model. That is input minus output plus or minus generation consumption, depending upon whether the material is getting generated, energy getting generated or consumed. We may have a sign convention here, and then rate of accumulation. So this is a very general mass or energy balance, and if the rate of accumulation is zero, then we end up with algebraic equations. And if the rate of accumulation is non-zero, then either we end up with ordinary differential equation or partial differential equation. So if the dependent variable is a function of only one independent variable, then we end up with ordinary differential equation. And if the dependent variable is a function of more than one independent variable, then it becomes a partial differential equation. And sometimes we also get differential algebraic equation coupled, differential equations are coupled with algebraic equations. And if it is a partial differential equations coupled with algebraic equations, then we end up with PDAE. So in any case, either we end up with ODE, PDE, or algebraic equations. Am I audible?
Yes, sir. Yes, sir.
Okay. So first I'll focus on the algebraic equations. So nonlinear algebraic equations. So in many problems in science and engineering, we many times need to solve nonlinear equations, algebraic equations. And when we equate the differentials with equal to zero, that is nothing but, in other words, we are trying to solve a steady state problem, that is time derivatives are zero. and we are trying to solve algebraic equations. Well-known examples are of algebraic equations are in thermodynamics, equation of state like RK equation, SRK, flash calculation. So these are the examples from thermodynamics where we need to solve nonlinear algebraic equations. And suppose we need to find out the steady state of CSTR or PFR or any other reactor, ideal or non-ideal. Basically, we are trying to solve nonlinear algebraic equations. In fluid flow operations also, friction factor calculation is a nonlinear equation. There we have square root of f term. And terminal velocity calculation also involves nonlinear algebraic equation solution. And in mass transfer also, pressure drop across the column is a nonlinear algebraic equation. Flow through, in fact, one of the simplest equation is flow of liquid over VL. It's also nonlinear algebraic equation. So the simplest mathematical model in chemical engineering is a nonlinear. We rarely have linear equations. In fact, we linearize nonlinear equations and we try to solve assuming that the system will behave as a linear system in a small operating window. But in reality, all the chemical engineering systems are nonlinear. So a number of times we need to solve nonlinear algebraic equations. So this is a small comparison between linear and nonlinear equations. This is a set of linear equations. It's Ax equal to b, very well known formulation of linear equations, and the x vector, that is unknown vector, can be obtained by inverting A matrix multiplied with B vector. We get unknown x, and it is a linear equation. And all of us know the degrees of freedom analysis, that is number of equations and number of unknowns. If it is equal, then it is perfectly specified, over specification, under specification, and depending upon the number of equations and number of unknowns, we may have unique solutions, or we may have no solution, or we may have multiple solutions. This is not the focus of today's talk. However, the linear equations can be solved by Gauss elimination, Gauss-Jordan value factorization, iterative. These are direct methods. Where iterative methods like Gauss-Seidel, successive over-relaxation, etc. Why this? I am just briefly telling, because in nonlinear solution also, the equation can be formulated as a linear equation, and we can use this technique to solve nonlinear equations. So nonlinear equations, these functions function vector f1 to fn is a nonlinear function, and it's a function of x vector. X is a vector of x1 to xn. In general, I am talking about even a simplest system will have more than one variable. If you talk about a reactor, then we have temperature and concentration as two variables. So the simplest system will be multivariable. So we have to deal with multivariable equations, nonlinear equations. So solving nonlinear equations means finding out values of unknown variables that make the function vector 0. That is steady state solution. So we should not be confused with finding out the values of x equal to 0. It is finding out f of x equal to 0. So finding the value of x vector that makes the function vector equal to 0. And as far as nonlinear equations are concerned, only iterative methods are available, such like successive substitution method. It is also known as fixed point iteration method. The Newton-Raphson, very well known technique. In most of the case, we use this Newton-Raphson technique. Then bisection method, secant method, regular falsing method, etc. So suppose you have some of the examples of scalar, that is single nonlinear algebraic equations, like suppose find x such that exponential x plus sin x minus 2 equal to 0. And another single variable example is y exponential y equal to 3. So we need to find out the value of this x or y that makes this function 0. So in order to make this in the standard formulation, this 3 is to be taken on the left hand side and equal to 0. Then we try to find out y that makes the function 0. In chemical engineering, we have Bernoulli equation for fluid flow in open channel with a small bump is given by this expression, which is a function of h. This flow rate, gravity, and some dimensions and some constants. So this is a nonlinear equation. We have h square here. It's a nonlinear term. So this can be this is a single variable example. And flash calculation is also single variable example. We have some feed with some feed composition, and when flash operation take place, vapor and liquid are in equilibrium, and this V, vapor fraction, is a variable that we need to find out. So solve for V that makes this f of V equal to 0. It's the flash calculation example. It is a nonlinear algebraic equation. And as I said, in most of the case, we have more than one variable. So it is known as a nonlinear system of equations. One example is f1x, x is a vector of x1, x2, 2x1 square plus x2 square minus 8, and x1 square minus x2 square plus x1, x2 minus 4. So this is how it is represented. X is a vector of unknowns and f is a vector of functions. And one example from chemical engineering is isothermal reactor, that is automotive exhaust that contains carbon monoxide, nitrogen oxides, and oxygen O2 that reacts catalytically in catalytic converter. And suppose you want to find out the steady state solution of this catalytic converter, right? And these are the dynamic equations, and if we equate this to 0, it becomes a steady state solution. And some dimensionless, these are the dimensionless equations where initial values are given 0, 0, 1 of dimensionless convergence of CO, NO, O2, that is Y1, Y2, and Y3 with some parameter. It is basically multivariable steady state problem. That also, it's a nonlinear system of equations. So with this brief idea about the single variable and multivariable nonlinear equations, these are the solution strategies. So nonlinear equations, when we try to solve algebraic equations, the equations may have one solution or it may have many solutions. Many solutions means it may have multiple solutions or multiplicity kind of behavior. Many of the non-isothermal CSTR or even distillation column have been reported to exhibit multiple solutions for the same set of input or initial conditions, since it gives different steady states. And solutions methods are iterative. All the methods are iterative, and all these methods require initial guess. So there is no guarantee that we get a solution, even if it is existing. The reason is that the choice of initial guess is very critical, very crucial to find the solution. And if we start with bad initial guess, then it may lead to no convergence or to an undesired fruit. So usually it occurs when we don't have system knowledge or partial knowledge about the system. For example, being a chemical engineer, if I try to solve some electrical or mechanical system equations, and if I don't have good knowledge of the system, then I may start with bad initial guess, and this may happen. And so if I have, suppose being a chemical engineer, if I try to find out if I try to solve this problem, flash calculation, so I should have the knowledge of the lower and upper values of V. Suppose it is a mole fraction or mass fraction, then the lowest value is 0, maximum value is 1. So I should not start with any guess that is beyond this upper and lower values. So system knowledge helps you to choose proper initial guess. And knowledge of the system, that's why it is very important for proper initial guess. There are two approaches used for solution of nonlinear algebraic equations, closed domain approaches, and open domain approaches. Closed domain approaches are also known as bracketing methods. So in this closed domain approach, we bracket the root, and then we try to reduce the bracket systematically. So it is a simple method. It's a robust because once the root is bracketed, the solution is guaranteed. But it requires to bound a root. That bracket is a must, and it gives you sometimes problems when multiple roots are bracketed. Okay, so the bracketing method, closed domain method, may converge to the root which is not desirable if multiple roots are bracketed. In open domain methods, bracketing is not required. These are more efficient methods, but less robust. Less robust means it may diverge. If you start with bad initial case, then open domain method may diverge. So, how to start solving nonlinear algebraic equations? Write the equation in this residual form. That is, all the terms you take on one side and equate the function to 0. And then, if you use bracketing technique, then you have closed domain methods, that is bisectional, regular, falsy methods. And if you do not bracket the root, then we have secant, Newton's method, or fixed point iteration methods, etc. So first, as all these techniques are iterative in nature, we need to stop our iterations at some point of time. So it depends on number of iterations allowed and rate of convergence. So sometimes if you start with bad initial case, then your solver or algorithm will go on iterating, and you don't get any output. So whether it is converging or not, or what is the problem, suppose you don't know. If you don't stop your iterations, then you will be waiting and waiting. So there has to be some tab on number of iterations. If the number of iterations are more than some value, predefined value, then the algorithm should report that the system, the technique has not converged. And then we also need to know what is the rate of convergence. That means how quickly the sequence, that is xn, where xn is approximate solutions that obtains by using numerical methods, and how quickly this sequence converges to true solution x star. So there are two types of convergence: quotient convergence, also known as Q convergence, and root convergence, that is R convergence. In Q convergence, it is defined in terms of ratio of successive errors. So when we do iterative calculations, the errors are usually defined as, in most of the real case, we don't have true solutions. So usually we compare the present approximation with the previous approximation. So absolute difference between the present and previous approximation is nothing but successive error, and divided by the present approximation, absolute value of the present approximation. So this ratio, in this ratio term, this Q convergence is defined, and it describes the convergence in which the overall error decreases with each iterations. Overall error means the error term is a vector, because most of the problems are multivariable problems, and for each variable we have error. So for n variables, the error vector will be of n size, and all the variables error should converge, should decrease. So sometimes it happens that some of the variables converge quickly compared to other variables. So the overall error means we have to make sure that all error vectors, all the elements of error vector converge, decrease with each iteration. That is what overall error. So the Q convergence is it's defined in terms of successive error terms, and it makes sure that overall error decreases with each iterations. Whereas in the case of R convergence, it is a weaker form of convergence, by the way. but it uses the characterize. It used to characterize the convergence rate of algorithms. Whereas here, it takes into account the errors, whether the error is decreasing or not. Whether in these case, our convergence, it takes into account of convergence rate of algorithms when convergence is not monotonic. Okay, so here in the Q convergence, the rate of convergence is almost constant, whether here rate of convergence is changing. So then question comes, what is the rate of convergence and all that. So let's go through very a little bit brief in little detail of these two convergence criteria. Q convergence, let x star is a true solution and xn is an approximate solution at n iteration, and the error at iteration n is norm of difference between x star minus xn, and the method, that is solution method that we use, it's said to be Q convergence with the rate k if limit n tends to infinity, that is number of iterations are increasing, the ratio of norms of x star minus xn plus 1 upon x star minus xn, and this is to the power k, it is equal to c, and where c is a finite and positive, and C is known as rate of convergence, and K is order of convergence. So if K is equal to 1 and C is less than 1, then it is said that the convergence is linear. So in other words, x star minus xn plus 1, that is present error and previous error, the present error divided by previous error, if it is less than 1, absolute value, and norm in fact, so it is linear. Okay, so this is a linear convergence. Error is decreasing linearly. Then if k is between 1 and 2, then it is said as superlinear, so faster than linear. And if k is equal to 2, it is said that it is a quadratic conversion, very fast convergence. Okay, so and in case of R convergence, the Q convergence definition have one shortcoming, that it do not include some sequences which converge reasonably fast, but rate of convergence is variable. It do not converge at the same rate. The rate of convergence varies. Okay, so Q convergence do not take this into account. So, and for that, the R convergence is used. So, if xn converges to x star, where x star is a solution, then it is said that to be R convergence if there exists a sequence En. Okay, this En, the sequence, it's such that the absolute difference between xn minus x star is less or equal to En for Rn. Okay, so here we don't talk about the rate of convergence, but we talk about some sequence, right? And this difference is less or equal to En for Rn. Okay, so these are some of the linear, superlinear, quadratic, or etc. Convergence rate. Okay, so here I talked about the norm. So some of you, most of you, I guess, must be knowing what is norm, but let's briefly go through what is norm. So a norm of a vector or a norm of a vector is a magnitude, measurement of magnitude of the vector, or you can say a size of the vector. Its notation is this, and common norms used while stopping the iterative calculation is one norm, two norm, infinity norm, or p norm. Where one norm is defined as this one. If it is written here one, then it is one norm. It's the absolute sum of all the entries of the vector x, and the two norm, that is Euclidean, also known as Euclidean norm, is square root of sum of square of individual elements of x vector. So in our this error, these iterative methods, after each iteration we calculate the error. So this will be the error vector. And if the error vector, so if one norm is this is less than some tolerance, it means that taking the absolute sum of all the elements, if the total summation is less than tolerance, that means individual entry will be less less than the tolerance. So this can be chosen as a stopping criteria. Similarly, 2 norm can be used to stop the iterations. Infinity norm is the maximum value of the entries of X factor, and P norm is also defined in this fashion. For example, suppose we have X factor like this, then one norm is absolute sum of individual elements, and 2 norm is a sum of square root of sum of squares, that is this value, and infinite norm is maximum value, that is 4 absolute value. And a norm of a matrix is nothing but a scalar measurement of square matrix magnitude. The norm is a scalar number, and notation is this. And common norms used for matrix are one norm, infinite norm, or Frobenius norm. One norm is column sum, absolute column sum. So individual columns of a matrix, you take the summation and find out the maximum of that. It is nothing but one norm. This is a raw sum. So all the rows, the individual entries of it, all the rows are summed up, and the maximum raw sum is absolute value, of course, is infinity norm. And Frobenius norm is the square root of sum of square of all the entries of a matrix. So these norms are used in stopping the iterations. Very convenient way. So now we start with first open domain methods. So the principle of open domain method is that you start from good initial or guess of the solution and iteratively refine the solution estimate. Convergence is faster than closed domain method, but diverge if initial guess is bad. So for example, suppose you start, in this case it's a convergence case, start with xk, then you get xk plus 1, from which you come back to the closer to the root. Whereas if you start with the wrong or bad initial case, then you may diverge. Okay, so this happens with open domain methods. So first method of open domain method is the successive substitution method. It is also known as fixed point iteration method, and many nonlinear equations can be formulated as fixed point problems. That is, x is equal to g of x, where g may be non. So this method can also be used for linear problems, and if g is a nonlinear, then it is a nonlinear algebraic equation problem. So what is a fixed point? A definition: a fixed point of a function g is any real number x for which g of x is equal to x. That is, a number whose location is fixed by gx. Okay. So suppose given f of x equal to 0, it can be defined as g of x is equal to x plus minus f of x. And some examples given here. Suppose fx is 3x squared minus x minus 2, which is equal to 0. It can be rewritten as g of x, that is, you take x on the other side. So what remains is 3x squared minus 2 is equal to x. Similarly, the second form, 3x squared minus 4x minus 2 can be written as you take x on the other side, so 3x squared minus 2 by 4. And here you don't have any x term, so you can add on both sides x, exponential x minus 2 plus x equal to x. So these forms are of this particular form, that is x on these x can be written as xk plus 1, and these terms are nothing but g of x. So once you formulate this g of x, then you can have the iterative scheme. It's xk plus 1 is equal to g of xk. Start with initial guess on xk and calculate xk plus 1. And after each iteration, you calculate the error term. And if error is less than the tolerance, you can stop the iterations. So very simple algorithm for fixed point iteration method. That is, xk plus 1 is equal to g of xk. X0, that is initial guess, is given. If it is not given, then we need to start with some initial guess, and it should be based on the system's knowledge. So iterate until xk, the absolute ratio of xk plus 1 minus xk by xk plus 1 is less than tolerance. The tolerance is determined by the user. It should be very small value. It's very simple algorithm. I will demonstrate two examples here. So f of x is exponential x by 2 plus x minus 1. And another problem is fx exponential x plus x minus 2. So let g of x for this problem be, you take x on one side. So what is left? Keep x on the left hand side. So on the right hand side, we have 1 minus exponential x by 2. And in this case, keep x on the left hand side. So we have g of x is equal to 2 minus exponential x. So these two functions start with initial guess point 2. Let's see whether they converge or not to the true solution. So very simple MATLAB program is written here. The first case is a converging case, that is g of x is equal to 1 minus exponential x by 2. Started with 0.2 value, I guess, yeah, 0.2 value, and it is slowly converging to the solution after some 20 or so iterations. And the second case, that is g of x, is a diverging case, 2 minus exponential x. It is diverging, it is not converging. So these are the two g and g1 I have written here, 1 minus exponential x by 2 and 2 minus exponential x. And a very simple while loop is used here to find out the solution. So one case is converging, the other case is diverging. So is there any way that, that we make sure that the method converges to the solution? Yes, we can always forecast the behavior of the iterations. So if G is a continuous in AB, and if G takes the values, G of x takes the values in AB for all x in AB, then G has a fixed point in AB. Okay. So in addition, differentiation of G with respect to x, that is G dash of x, if it exists on AB, okay, and a positive constant which is less than 1, that is k, less than 1, exists with absolute value of differentiation of G with respect to x, which is if it is less or equal to k, that is k is less than 1, then for all x from A and B, in A and B, whatever value you start with x from A to B, there is at least one fixed point in A and B. So if this condition is satisfied, then whatever g of x you choose will converge to at least one root. Okay. So if we check this condition whether it is true in this case or not, okay, so this is the g of x, and differentiation of this g of x will be minus exponential x by 2 will be 1/2, and here it will be minus exponential x, and if you put the value of 0.2 here, then minus exponential 0.2 will be more than 1, right? So absolute value will be greater than 1. That is why this term is, this g of x did not converge, whereas this is less than 1, so that's why it is converging. Its differentiation with respect to x is there. You can see it is divided by 2, so whatever we get is going to be divided by 2. So that's why it is converged. So the extension of this fixed point iteration method to multivariable case is very straightforward. Suppose we have system of nonlinear equations, and in compact form we used to write f of x equal to 0, where f is a function vector and x is unknown variables vector and 0 is a 0 vector. And for fixed point method, this can be written as x vector is equal to g of x. So iteration scheme can be formulated as xk plus 1 is equal to g of xk, where k starts from 0 to n number of iterations. And for this formulation, this g formulation, whether it is going to converge or not, we need to make sure that Jacobian, the norm of the Jacobian matrix evaluated at x should be less or equal to 1. Right? So let's go through one example. We have two functions f1 and f2. X is a vector of x1 and x2, and initial case is zero point 0.5, zero point 0.5, and we have two choices of,
Excuse me, sir.
yeah,
Actually, the I just want to ask from fixed point iteration methods.
yes,
So there, you wrote the fx can be the written as a gx, right? So gx is again a nonlinear function, right?
yes.
So in that means how do we start actually to find the root by something like a some Gauss serial type of thing, or we
No,
can keep a some trial value of x and keep on
no,
solving till
no,
we get the
no, no, no. It's not Gauss settle. It is a very simple iterative scheme. See, see, see. This is the choice for. So, okay, let me show you first simple problem, this problem. So we have g of x is equal to this, right? That means x
correct.
x k plus 1 is equal to 1 minus exponential x by 2 k. Here we have x k plus 1 is equal to 2 minus exponential x k. So gx is, here this g of xk is 1 minus exponential x by 2, and this case it is 2 minus exponential x. So on the left hand side we have x, xk plus 1. So if I have initial case that I put here and I operate g function on this, that is, and it gives me the value of xk plus 1. Similarly here, so once I get xk plus 1, then I calculate this, and then if it is less than tolerance, then I have to simply stop the algorithm. It's very, this
Okay.
fixed point method is only one function evaluation. This G is different from F. So there are
Hmm.
guidelines of how to choose G that make sure that the convergence is obtained. I hope it is clear.
Yeah. Okay. Fine.
Okay. So here we have two choice. The first choice is simply this minus 8x1 is written as minus 7x1 minus x1, and one x1 is taken on the left hand side, that is x1k plus 1, and 2x minus 2x1 cube minus 7 instead of 8, now I will write minus 7x1 and remaining term. And similarly for second equation we have this choice, and another choice is given by this. So at x0, that is at k equal to 0, I put value of x1 and x2, that is x1 and x2 in this equation, two equations. I get x1 1 and x1 x2 1. And once I get this, then I compare this vector x1 x2 k plus 1 minus x1 x2 k, that difference divided by the vector, that is x1 x2 k. It's a norm. So that norm, if it is less than some tolerance, then that is okay. If it is not, then you continue your iterations. In the next iteration, whatever xk plus 1 we get becomes xk, and new value of x k plus 1 is calculated. So there are two choice of g of x we have, and choice number one, it is diverging. You can see, though it is written y2 and y3, it is actually x1 and x2 only. And you can see x1 is diverging. After four iterations, it has from started with zero point 0.5, it is jumping negative, positive, etc. So oscillations are observed. Whereas the second choice, after some 80 iterations, it has converged almost the similar values we are getting. And I have shown only this choice number two is a simulation results, not number one, first one. So x1 and x2 both are converging to the solution. And this is the norm, xk plus 1 minus xk divided by xk plus 1, norm of the error vector. That error is also almost becoming zero. So why this happens? Let's check whether this is true or not. If the norm of the Jacobian matrix of G function, uh, multivariable G vector, G function vector, if it is less or equal to 1 or not, okay, for these two choices. Choice number one, for choice number one, the Jacobian is given by minus 6 x1 square minus 7 4 minus 4 2x2 plus 4x. We can check if you want. And these are the two functions right hand side. So I have just simply found the Jacobian for choice number 1 and choice number 2. And in this Jacobian, if I put x0, that is 0.5 value for x1 and x2, then the beginning itself, the Jacobian of choice number 1 is greater than 1, 11 point, absolute value, of course, it's a norm, remember, norm of this matrix. So it is 11.11 something. And for second choice, it is less than 1. So this is the reason why the second choice is converging to the solution, whereas the choice number 1 is diverging. So
So how
this
this actually 20 and 24 came into the picture actually? This choice came
yeah,
from there.
choice is, so there are guidelines. There are guidelines to choose the proper g of x. Okay, so the xk. So this xk plus 1 is equal to f of xk, right? G of xk. Okay, so this can be written as xk plus beta f of xk, and this beta is a tuning parameter. So we can exactly find out, we can choose the value of beta that makes sure that this function f, g of x converges to the solution. In fact, the sufficient condition that is, this is condition, sufficient condition is this condition, we exploit this condition to make sure that g of x converges. So you may refer this. It's a simple technique. In fact, you choose the beta. It is for single variable function. It is explained here, but for multivariable also you can have similar extension. So there is a way to choose appropriate g of x. The simplicity of this method is that you don't have to find out any differentiation or anything. It's very simple iterative scheme. The only issue with this that its convergence is not fast rate of convergence compared to Newton-Raphson. So I hope it is clear. So now we move to the Newton-Raphson method, which is discovered independently by Joseph Raphson and Isaac Newton almost at the same time. And however, it was first published by Joseph in his book, and it is perhaps the most widely used of all the root locating methods. The reason being the fastest convergence rate. The rate of convergence of Newton-Raphson is quadratic. So this is a graphical explanation of Newton-Raphson method. You start with initial case xk. So evaluate f of xk. This is your function, and this is the true solution. The value of x at which f of x becomes 0. So from this point, you draw a slope. Okay, that is f dash of x. That gives you the next value of x, that is k plus 1. And having the k plus 1, you evaluate f of x k plus 1, and again find out the next value of xk plus 2. So this way, slowly you converge to the root. Okay, so now this is so in Newton-Raphson method, the algorithm is like this: the initialization, choose the initial point x0, initial guess, then choose stopping tolerance, which should be obviously greater than 0, and maximum number of iterations should be there. If you don't choose this, and if the initial case is not good enough, then your algorithm will go on iterating and iterating. So if the maximum number of iterations are reached, and if the convergence is not obtained, then the user should come to know that the initial case is not good enough. Then set the iteration count, that is start with 0. Then after initialization, how to stop the iterations. If absolute value of f of xk is less or equal to tolerance, by tolerance, this is stopping tolerance, starting value, but actual tolerance is very small value, should be close to 0. Because absolute getting absolute 0 in most of the numerical schemes is not possible. So we choose very small value, 10 to the power 8 or 10 to the power minus 6, etc. And or if the ratio of xk minus 1 upon xk, the absolute value. If it is also less or equal to tolerance, then also the iteration should be stopped, assuming that xk is the solution, or the number of iterations are greater than, or suppose it has reached the maximum number of iterations, then also the iterations are to be stopped, because at nth iterations it is not necessary that the xk is the solution. The error might be still greater than tolerance. So if the iterations have reached the maximum value, and if this condition has not satisfied, then probably your initial xk, initial point is wrong. You should change. One should change the initial case and restart the algorithm. Then the function and derivative evaluation is required, f of xk and f dash of xk, and then Newton-Raphson step number 3, the compute the Newton-Raphson step, that is the delta x is equal to minus f of xk upon f dash of xk, and then update the iterate. The next value of xk, x is xk plus 1 is equal to delta xk plus delta x. Delta x is given by this, and then increment the counter, update the iteration number, and return to state number 1. So these iterations continue till the stopping criteria is satisfied. So the problem that diverged in case of single variable problem, this problem 2 minus exponential x, okay, the same problem, that is this problem exponential x plus x minus 2, that we tried here with Newton-Raphson method with different initial cases. Okay, x0 is 0, x0 is 5, x0 is 10. In all the different initial cases, it is diverging, it is converging to the solution. You can see this is with initial case 0, then 5 and 10. The actual solution is true solution is 0.4485, and these are the function evaluations. Function evaluation, function value is also approaching to 0 as the number of iterations are increasing. One thing we can observe here, that if you start with initial case that is far away from the true solution, it will take more number of iterations. If your initial case is close to the true solution, then it will take less number of iterations. So this is a single variable example for Newton-Raphson method, and yeah. So how to make sure that Newton-Raphson converges to the root, because this is an open method. Bracketing of the root is not considered here. So if sometimes happens that if the step size is very large, then instead of this you may go somewhere here depending upon the function behavior, and the algorithm may diverge. So in order to make sure that you take small steps, okay, the alpha parameter is added here, alpha parameter, that is known as relaxation parameter, and its value is between 0 to 1. An adaptive strategy can be used here, that select a suitable value for alpha. So if alpha is equal to 1, it is a usual Newton-Raphson method, a full step Newton-Raphson method. And if after keeping alpha equal to 1, once you calculate xk plus 1, then try to evaluate the absolute value of f of f function evaluation at xk plus alpha delta x, and check whether it is less than f of xk. If this is true, then this step with alpha equal to 1 can be accepted. If not, if this is wrong, if it is not true, then you can reduce the alpha by 1/2 alpha, and this step is repeated. Repeat from this step. Again, evaluate f of xk and this one, and this you can continue. So, in other words, we are moving towards the solution very slowly. The Newton-Raphson step is reduced. Okay? So slowly we are moving towards the solution. We are making sure that Newton-Raphson is not going away from the solution. So in Newton-Raphson method, we have to evaluate the differentiation, derivative of the function. And sometimes it is difficult to find out the derivative of the function. So derivative of certain function may be extremely difficult to obtain or inconvenient, because sometimes a function is near maxima or minima of a function, that the derivative will be zero or it will be close to zero. So if the iterations are going on, and if the iteration has reached to near the maxima or minima of the function, then it will take large number of iterations, and there will be some oscillations observed in the xk plus 1. So, in order to avoid this problem, that is derivative, sometimes it is difficult, and if the derivative, if the denominator, if it is a maxima or minima, derivative itself is a zero at exact value of maxima or minima. But near the maxima or minima also, the derivative will be difficult to find out. And in case of multivariable problem, the Jacobian matrix will become close to singular. So, in order to avoid this issue, and the approximate derivative of f dash is used by using backward finite difference. So, f dash of xk is approximated as f of xk minus f of xk minus 1 divided by xk minus 1. And in Newton-Raphson method, this f dash of xk is replaced by this term, and what we get is secant method, so or secant formula. So here we don't need to find out derivative of a function, but at each iteration, when we start, we need to find out two function evaluation. But later, after the first iteration onwards, only one function evaluation is required, because one of the previous function evaluation is used in the next iteration, as xk plus 1 becomes xk for the next iteration. So a new iterate in secant method depends on two previous estimates, xk and xk minus 1. So when you start with x0, you require x minus 1 to calculate x1. And only one function evaluation per iteration is required, and derivative is not needed. Because once we calculate x1, okay, in order, when we go for calculation of x2, x1 becomes x0 and x0 becomes x minus 1. Or this becomes xk minus 1 and x1 becomes xk. And this is way, so already in the previous step iteration, the functions evaluation have been carried out. So those values can be stored, or it can be used in the next iteration. So only one function evaluation is required, and no derivative is required in secant method. So secant method is stable, is more stable than Newton-Raphson, but convergence is slow convergence. It's not quadratic, but better than linear. So algorithm is similar to Newton-Raphson. However, we have to choose 2 points, x0 and x minus 1, and stopping criteria or stopping tolerance, and maximum number of iterations, and iteration count. Then function evaluation in the step 1, compute f of xk, and stopping criteria is similar to Newton-Raphson. Then you calculate the secant step, that is delta x, that is minus of f of xk upon f of xk minus f of xk minus 1. Yeah, there should be one more function evaluation here, f of xk minus 1, only when you initialize. But after that, only f of xk is required, because f of xk minus 1 is already calculated in the previous iteration. So only one function evaluation or iteration is required. So delta x, calculate, and then update the iterate, and increase the number of iterations by 1, return to step 1. So this is very much similar to Newton-Raphson, but only when you initialize, we require 2 initial case, and during the iterations, no derivative is required, and only one function evaluation is needed. So same problem, exponential x plus x minus 2 with 2 different initial cases, x0 equal to 5 and xn, x minus 1 equal to 10 has been assumed. And these are the iteration steps. And we can see that though the Newton-Raphson is faster, converging less number of iterations here also, but secant is also converging, slightly more computationally expensive than Newton-Raphson, but it is converging. The advantage of secant method is that you don't require to calculate derivative. So now with this, we extend the Newton-Raphson to multivariable case. As I said earlier also, most of the problems are having more than one variable. The simplest problem is also multivariable problem. So we have in most of the case nonlinear system of equations, and first we consider the two-dimensional case for the sake of brevity, and then it can, whatever analysis we go through, it is applicable to n number of equations. So in matrix vector notation, this function vector can be written like this, and x vector is written by this, and let root r is r1 for first equation, r2, r1 and r2 are the values of x1 and x2 for which this function vector becomes 0 at root r. So let x0 be the initial case for the solution vector x, and let the root r be at the small, slightly away from the true solution by value delta. So x0 is initial case plus delta is equal to r. So this initial case is delta away from root. That's what we assume here, and we consider bivariate Taylor series expansion of fx around x0. So f1, this is a new Taylor series expansion of f1 and f2. So x1 0 plus delta 1, x2 0 plus delta 2, etc. This f1 and f2 are function evaluations at initial case. So these are the numbers. Then this is the partial differential of f1 with respect to x1, partial derivative of f with respect to f1 with respect to x2, and then higher order term similarly for second function. Since delta is a small number, the higher order terms can be neglected, and also we have r, which is a root, and x0, which is equal to x0 plus delta, and f of r is 0. So left hand side, the left hand side is actually f of r only, x plus delta. So left hand side is 0, and right hand side is all the terms are actually numbers except delta, because these two are the function evaluations at initial case. So this becomes a number. The partial differential terms are also evaluated at x1 and x2. Okay, so these are the numbers except delta 1 and delta 2. So basically these are the linear equations. These two linear equations in two unknowns, delta 1 and delta 2. So in matrix vector form, 0 is equal to function vector is equal to Jacobian matrix. This is known as Jacobian matrix, and the delta vector. So in compact form, 0 equal to f plus j delta. This is to be evaluated at x0 or xk, you can say, for xk plus 1, xk. So it is easy to find out delta now. So delta can be obtained by solving this linear system of equations. This is a linear problem. Okay. So delta is equal to minus j inverse f. You take f on the other side, it becomes minus f, and then delta is equal to j inverse f. J inverse f. So given x0 initial case, the algorithm consists of evaluating the function and the Jacobian at xk, and solving the linear system of equation for delta. Once the delta is obtained, then the estimate can be obtained, that is xk plus 1. That is xk plus 1 is equal to xk initial case plus delta. So where delta is minus j inverse fk, and iteration starts from 0 to n, and during the iterations, this Jacobian matrix should be non-singular. Okay? If it becomes singular, then we cannot continue with Newton-Raphson method. It is difficult. It is not possible to find out inverse of a singular matrix. Even if the matrix is close to singular but not singular, then also it creates a lot of problems. So let's see one example, two variable problem. Xk plus 1 is equal to xk minus Jacobian inverse into f of xk. So x1, x2, k plus 1 is equal to xk minus, this is Jacobian matrix of these two functions, and two function vector is f. And at given initial case, okay, so x1 is equal to x0, and by putting the value of x1, x2 initial case in this expression, we have this matrix, and This is what we get as x1, started with 0, 0 as initial case. The final answer of this problem is this one, and these are the iterations. So, so, uh, Newton-Raphson's convergence is guaranteed if we start with a good initial case, and for good initial case, it requires very good system knowledge, quadratic rate of convergence, which is very fast compared to other methods. Relaxation parameter alpha can be used here also. And there are some issues, however, with particularly with Jacobian matrix. The singularity of Jacobian matrix, if it is the case, then we cannot continue. And sometimes, if it is not singular, but if it is ill-conditioned, means it is close to singularity. By the way, the condition ill conditioning or condition number of a matrix is defined by the multiplication of norms of matrix and its inverse. So if the condition number is very large value, then it is said to be in condition. And if that is the case, then there is an issue with the Newton-Raphson method. And this issue can be handled by using the approximation of Jacobian matrix by standard methods like BFGS or DFP, Broyden's method or David Fletcher method, Powell's method. So it approximates Jacobian every time we don't need to find out Jacobian matrix. So with this, I think I have covered closed, open approaches. And after then we move to the closed domain methods. Closed domain methods are also referred as bracketing methods. It is based on the fact that the function undergoes a sign change in the near vicinity of a solution x of f of x. Near the value of x star, if you evaluate f of x of a slightly higher value of from the x star and smaller than the x star, then we may find that fx is having different sign, plus and minus. So start in the bracketing is required, that is known as closed domain. Start with two initial points known as lower bound and upper bound, that is xl and xu, and make sure that the true solution is bracketed between lower and upper bound. And we can make sure by checking this condition, that is function evaluation at xl into function evaluation at xu. If it is less than 0, then at least one of the function evaluation is negative and one is positive, then only this will be less than 0. Both are negative, then this will be positive, and both are positive, obviously it will be positive. So one value has to be negative, then only this condition is satisfied. So once we bracket the loop, then reduce the bracket systematically. Right? So for that we have two methods, bisection and false position. Okay. So in bisection method, bracket the solution and then make sure by making sure this that this condition is true, and then bisect the bracket. So that is find the midpoint. Xm is equal to xl plus xu by 2. And once you have xm, then you check these three conditions. If f of xl into f of xm is less than 0, then the root lies between xl and xm. So xl is retained and xu is replaced by xm. If f of xl into f of xm is greater than 0, the root lies between xm and xu. Then xl is replaced by xm and xu is retained. So this way, you after finding xm, calculate f of xm, then check this condition. Accordingly, you go on changing this, and once you change this, once you find the new value of either xl or xu, then again xm is to be obtained, and again this condition is checked. So if f of xl into f of xm is 0, then the root is xm. We can stop the iterations. In fact, absolute 0 is very difficult to obtain. So we define some tolerance, which is smaller value, and if this ratio, either this or this, is less than tolerance, then the iterations can be stopped. In fact, this xm, if you write in this term, then we get this expression. So these two are nothing but equal values, equal to each other. So bisection method is also applied to the same problem. F of x is equal to exponential x plus x minus 2, starting with x1 and x2 as 0 and 1. As in this case, we know the solution 0.437, but always you can check f of xl into f of xu. If it is less than 1 or less than 0, then root is guaranteed to be bracketed. And we can see that xl and xu both approach to the same value, that is nothing but the root. So in bisection method, the function must be continuous. It should not be discrete. And the calculations are very straightforward. It is easy to implement. Convergence is guaranteed. However, it takes more computational efforts. Number of iterations are more because the convergence rate is not as Newton-Raphson method. Then false position is also known as regular falsy. It is actually secant method, but secant method you can say is secant with bracketing of the root. So this is the secant formula, and if we assume that bracket is already there, we have already bracketed the root between xk and xk minus 1, okay, by making sure that one of the function evaluation is less than 0, so this multiplication will be less than 0. That's so bracket is there. So when you calculate xk plus 2, okay, when we have bracketed the root xk plus 1, we are going to calculate using the secant formula. But then for the next iteration, when we go for xk plus 2, the iteration proceed in either of these two directions depending upon these two cases. That is f of xk plus 1, if it is less than 0, then xk plus 2 is equal to xk plus 1, and here we replace xk by xk plus 1, and this xk, the xk minus 1 is replaced here, and if it is greater than 0, then we have this expression. So here we make sure that the root is bracketed, and depending upon, so every time you make sure this condition in each iteration, and depending upon this, so xk plus 2, when you go for xk plus 3, this will become xk plus 2, xk plus 2, and if it is less than 0 or greater than 0, accordingly this formula is changed. So either of this one formula is used, and this becomes regular falsy. So since this is bracketing technique, it is going to converge. Okay, so let's go through very quickly one chemical engineering example. Consider a CSTR with a single first order exothermic irreversible reaction A gives B with a rate expression given by this, and mass and energy balance equations are given by this. So if I equate dCA by dt and dt by dt equal to 0, it becomes a steady state problem. So for steady state solution, we have two functions, F1 and F2, mass balance and energy balance function, and Jacobian matrix for this system is dou f curly F1 by curly CA, curly F1 by curly T, etc. And this is the Jacobian matrix obtained for the system, and these are the values of Jacobian matrix. So let me quickly show you the So if I use my own program, it's very simple program, convergence, tolerance, etc. So if I use my own program, then with a different initial gaze, okay, 9, 300, 5, 332, 360, if I use first initial gaze, right, then the solution that we obtain is this one, right? That is 8.56 and 311. Okay, and if I use different initial case, okay, so remember that we have not changed any input parameter of CSTR, only initial case we are changing, and if we choose a different initial case, then also we get the same solution. However, if I select the another case, okay, then I get different solution, different steady state solution, which is different from the previous two. Now, the MATLAB is having inbuilt nonlinear solver, that is fsolve. And if I use the first initial case, then what I get is what I get is different. The first steady state is the same as what we obtained, 311 and 8.56. And if I use another case, this case we have used with simple program that I wrote. So I get different solution than the previous one, 339 and 5.51. And if I use the third one, I get the same solution as I got with this program. So point that I'm making here is that MATLAB's inbuilt fsolve solver program is very powerful compared to the simple Newton-Raphson program. Okay, so all the three steady states are obtained using fsolve. So this CSTR is having different steady states for the CSTR. This CSTR without changing any input parameter. Okay, with the various input parameter, we are just changing the different initial guess, and with three different initial guess, we get different steady states. So that is also known as multiple output multiplicity. For the same input, we have different steady state outputs. So we can solve similar problems to find out the steady states of a plant or more complex than this. Okay. So with this, I move to my next topic, ODEs and PDEs. Okay. So I can take, or at the end, we will take some questions. Okay. So ODEs, some classification will be there, initial value problem and boundary value problems. We'll be discussing, and numerical schemes, and finally partial differential equations. So as I said earlier also, that based on the first principle, when we develop any mathematical model, when this term is not zero, we end up with ODEs or PDEs depending upon, and sometimes DAEs or PDAEs. Very quickly going through the classification of ODEs based on the order, first order ODEs or second order ODEs. Whether it's linear or non-linear. If the function is non-linear, then it becomes non-linear ODE. Linear is a very simple A into 1. Explicit or implicit. Explicit, the dy by dx is equal to this, but if the solution depends on dy by dx itself, okay, and becomes implicit problem, then dimension based on dimensions, one-dimensional problem, multi-dimensional problem, in the vector form dy by dx is equal to ay. Some examples, liquid storage tank, very simple example, liquid flow engine going out, we have a wall, volume is equal to area, same cross-section area is constant, so volume is equal to A into H. Mass balance gives us this rho A dH by dt, inlet minus outlet. And if this wall characteristic is linear, then WO can be replaced by CV into H, where CV is a discharge coefficient, and the outlet linearly dependent on H. And if the WO is given by nonlinear relation, which is reality, CV into square root of H, then it becomes nonlinear ODE. And just now we checked, we have seen the CSTR problem. Now we are not interested to find out the steady state, but we are interested to find out the dynamics of the reactor. Then plug flow reactor example, that is also a dynamic problem. Rate of change of concentration as a function of distance, that is Z direction, is a differential problem. So by the way, in plug flow reactor, the ideal plug flow, the variation of Ca across the radial position is 0. There is no variation in ideal plug flow reactor. So that's why we have ODE only. But if it is a tubular reactor, not plug flow but tubular reactor, then concentration will not only vary with Z but also in radial direction. So it becomes partial differential equation. So in vector presentation, two-dimensional linear problem, dy1 by dx, dy2 by dx is equal to this. So y is equal to y1, y2, dy by dx is given by this. And if it is non-linear, then this is the way we write in a vector representation. And for n-dimensional linear problem and n-dimensional non-linear problem, we write in this fashion. So OD, same example, exothermic CSTR in vector representation. These two are different scalar representation, but in vector form we write our variable vector as CA and D and function vector as right-hand sides of these two equations. And dy by dt is equal to f of y and initial condition CA of DO as a vector. Okay. Now, for ODE, any nth and most of the numerical schemes are, in fact, all the numerical schemes are available for the first order ODEs. So suppose we have nth order ODE, then how to deal with any nth order ODE can be converted into first order n ODEs. So in this simple example, it is explained. Initially, we have third order ODE, but if we let y1 is equal to y and y2 is equal to dy1 by dx, that is dy by dx, and y3 is equal to dy2 by dx, that is in terms of y it is d square y by dx square, then this equation is written as dy3 by dx, where y is the differentiation of d square y by dx square, that is d square y by one more differentiation of this is something but dy3 by dx and 2y3 similarly. So we originally third order ODE can be converted into first order system of ODEs, three ODEs. Third order is converted into, so nth order is converted into n first order ODEs. And now this can be solved by numerical schemes. So that's why most of the schemes are available for first order ODEs. Okay, so there are two basic approaches for solving ODE IVP. Taylor series expansion based methods like Runge-Kutta methods and polynomial interpolation based techniques such as multi-step methods. It is also, and predictor character methods are also there, collocation based methods are also there. So once you have polynomial or interpolant, okay, then that interpolant can be differentiated, it can be integrated, so you can do lot once you have developed the interpolation. Interpolant is, if it is available, you can do many things. So these methods are also very famous. Okay. So Taylor series expansion based method like Runge-Kutta method, how it is developed, let's go through quickly. Suppose you have scalar case dx by dt is equal to f of xt, and we have exact solution x star at time t, and that is x star n. Then we can compute the x star n plus 1, that is slightly away from x star n by one value, that is next value, you can say next value of x star by Taylor series expansion. So x star plus h, that is delta x, you can say dx by dt plus 1 by 2 factorial h square, etc. And this dx by dt is nothing but f of xt, and this term can be written as this. So for numerical solution also, the approximate solution can be expanded using Taylor series, and depending upon the truncation of this Taylor series, we get different schemes, numerical schemes. Okay. So, and in case of polynomial-based methods, also known as multi-step methods, we have the information of x and f from initial. Suppose we have this data x0 to xn, and f0 corresponding f0 to fn data is available. These are the data numbers. Then we can fit polynomial of desired degree, and that polynomial can be extrapolated for one step ahead. From up to xn we have the information available, and xn plus 1 can be obtained by using this polynomial. That is one step ahead prediction, you can say. Okay, so based on again the degree of the polynomial, we get different schemes like Euler's technique, Adams-Westphal, second order, third order, fourth order, etc. And in fact, this Euler's technique is first order Adams-Westphal, in which why it is known as explicit, because yn plus 1, that is next value of y, depends on the previous values of y, yn or yn minus 1, etc. In case of implicit formula, yn plus 1 depends on yn plus 1 itself, right? So we'll see that in brief after some time, after a while. So this is very simple. Given initial guess or initial condition of yn, you can find out next value. However, from this second order onwards, initial value y0 suppose given, then it is not, we cannot start solving yn plus 1 right from the first value, that is y0, because it requires the previous value. These formula are obtained by polynomial, and we have up to x0. We don't have xn minus 1 value, right? So the second order onwards, all these formulas are said to be having starting problem. So whenever we have starting problem, use lower order method. Suppose you want to use Adams-Westphal second order method. So in order to usually initial condition is given to you yn. So since yn minus 1 is not available, use lower order method to find out n plus 1. Once you get n plus 1, and from second iteration itself, you will be able to use second order method, because yn plus 2, when you calculate, this will be yn plus 1. This yn plus 1 is obtained by Euler technique, and yn plus 1, when you put here n plus 2, this is n plus 1, and yn is already given. So from second step onwards, we can use this. Similarly, if you use third order method, then it requires minus 1 and minus 2. So here again, you start with, when given yn, you start with Euler method, generate n plus 1. Then at yn plus 2 also, still minus 1 term is there. So there also we are not able to use this. So you go for lower order, not the lowest one. So in order to calculate n plus 2, use Adams-Westphal, and then from n plus 3 onwards, you can use this. Similarly for the fourth order method. So a simple problem is demonstrated here. Integrate dy by dt is equal to minus 3y. y0 is given as 1, and step size is given as 0.025, and final time is given as 0.25. The exact solution is y is equal to acceleration minus 3d, and we can see that Adams-Westphal, so first order, that is nothing but Euler's method, second order, third order, fourth order, and exact solution. And these are the actual numbers obtained. So in fact, none of the value is exactly matching with the exact solution. The reason is that all these methods are having some errors. So this last term, that is order of zeta, these are the error terms. In fact, when we use these equations, we don't have to use this. Okay? Only Euler method is yn plus 1 is equal to yn plus h f of yn. That's what we are used to. So I have just added this error term to show you that these are the error terms. So because of some errors, these errors, we have these errors. Right? So this is very simple problem. In fact, when you try to solve the real problem like distillation column or some other problem, you will really find a difficulty by using these methods. CSTR problem, this is the Euler's formulation. Okay. CAN plus H step size into f of CAN. And with this step size and number of iterations, very simple. This program is not written by me. It is available in UMass website. And this is the Euler solution. And if you use MATLAB inbuilt function ODE23, then this is the comparison between Euler and MATLAB ODE23. Okay. Now, I talked about implicit formula. So there are some problems which depends on yn plus 1. In order to calculate n plus 1, you require the value of n plus 1. Okay, so this kind of problems are known as implicit problems. A very typical example in chemical engineering is a distillation column, in which on each tray we assume the vapor-liquid equilibrium and mass balance and energy balance. So when you write mass balance, you require the vapor composition, and these vapor composition values are obtained by solving flash calculation. So flash calculations involves the initial guess. You have to guess, given the temperature, given the pressure and liquid composition, the flash calculation calculates the vapor composition and equilibrium temperature. and and so in order you have to guess the value of y, then iteratively you have to solve. So it is a inherent implicit problem. So these formulas are obtained based on Newton's backward interpolation formula, and again, depending upon the truncation of this series, we end up with different formulas. So in implicit Euler, then there are many formulas, but I have covered only those methods which are frequently used and well-known methods. So Crank-Nicolson and Adams-Moulton method. Here you can see some starting issues, n-1 and n-2 is there. So whenever these problems are there, you go for the lower order. Then from a particular iteration count, you will be able to use the exact formula. So let's go through one example using implicit method. Of course, this dy by dt is equal to sin y is not an implicit problem in reality, but for the academic purpose, we use to demonstrate how to use implicit method. So given y0 is equal to 2 and step size 0.05, obtain y1. So this implicit formula is rewritten as a function of n plus 1, that is yn plus 1 minus yn minus h sin yn plus 1 and 0. So it becomes algebraic problem, and this algebraic problem can be solved by Newton-Raphson or fixed point iteration method. So point here is that given the initial condition yn, from yn to yn plus 1, going to calculate yn plus 1, in between you have to use iterative calculation, you have to solve algebraic, nonlinear or linear algebraic problem. So this is the Newton-Raphson formulation for this problem. This is a function. So yn k plus 1 is equal to yn. So yn plus 1 is a variable. So yn plus 1 k minus f of yn plus 1 k by f dash of yn plus 1 k. So this is the function. That's what I have written here, and its differentiation. So it is negative. So we have positive sign here, and by putting the value of step size and initial gaze, etc., it becomes this. So this is after 4 iterations, it converges to this value. So point is that given y0, y1 is obtained, and in between from y0 to y1, these many iterations are involved. So from y1 to y2 again, it's a dynamic problem, dy by dt. So from y1 to y2, when you want to calculate, again the same iterations are to be repeated with different initialization. So implicit method is more involved. It takes more number of iterations, and so implicit method required to solve the nonlinear algebraic equations during each iteration, each time step. So there is another simple method for implicit function, which is known as predictor-corrector combination. It is basically a combination of explicit and implicit techniques. So for example, first order PC combination, if I talk about, then the explicit Euler is a predictor, and implicit Euler is a corrector method. So y bar is a predicted value of yn plus 1, which is used in corrector. So this is actually the implicit formula, but here we use y bar, which is obtained by predictor. That is explicit formula. So similarly, fourth order combination. So whenever any PC combination is to be used, use the same order of predictor and corrector. The reason is that if you use different orders, then different formulas are having different order of inaccuracies. So in order to make the accuracies of same order, we should use same order of predictor as well as corrector. So this is the same problem, this dy by dt problem. Sin y is solved by different methods: PC, predictor, corrector, Euler's method, Runge-Kutta, and Euler's explicit. See, Euler explicit, still it is solving this problem, because the problem that I have taken is very simple problem. But if you really take the real distillation kind of problem, then the problem will be realized by using this explicit Euler. So Runge-Kutta, I hope all of you know. So I'm not going to discuss Runge-Kutta methods, as time is also, we have very less time left, and a lot of things are to be covered. So I hope the organizer, uh, uh, can I extend 5 or 10 minutes if you allow? 5 or 10 minutes?
Uh, no problem, sir.
Okay, thank you. Thank you.
Yes, sir, sure.
Okay.
Yeah, yeah.
So, so so multivariable extension of these methods is very straightforward. Euler's multivariable extension is y1 to ym plus 1 is equal to y1 and ym h step size f1 to fm, etc. So in vector form we can write this, and Runge-Kutta extension is also straightforward. The problem that we face when we have multivariable system is a choice of step size. So there we face the stiffness problem. So many times people talk about stiffness of system. So stiffness is nothing but, in a simple words, I can say that some of the variables are changing very fast and some of the variables are changing very slow. In our chemical engineering examples, if I talk about, the flow dynamics is very fast. If you change the flow rate a little bit, immediately the final value will be attained. But if you change the temperature, inlet temperature, or if you change the inlet concentration, the concentration dynamics or temperature dynamics are slower than the flow dynamics. Similarly, pressure dynamics are slower than the flow dynamics, but faster than the temperature or concentration dynamics. So when we have fast and slow dynamics involved in a system of equations, and if we choose the same step size h for solving all the variables y1, suppose y1 is temperature, y2 is concentration, y3 is a flow, etc., then some of the yi's are changing very fast and some of the yi's are changing at very slow rate. And if we choose the same step size for solving all these dynamics, then if the step size is too small, then it is possible that very fast dynamic can be captured, but slow moving dynamics will take long time. And if you choose a large step size, then then the fast moving variable uh, dynamics cannot be captured. So it is known as a stiff problems, and stiffness is measured in terms of the eigenvalues. So it's a difference between the magnitudes of smallest and largest eigenvalues, and small step size requires to maintain the numerical stability of stiff problems. And when we have nonlinear ODE systems, dy by dx and dz by dx, two variables x and y, y and z, and this parameter, it is very small than 1. So it means that this dynamics, this rate of change of z with respect to s is very small compared to dy by dx, which is very common in chemical engineering systems. I just explained you with temperature, pressure, etc. So slow and fast physicochemical phenomena leads to highly stiff problems, nonlinear problems, and there we require specialized methods that takes into account the variable step size and variable order. So this method which we talked about are orders. Once you fix the order, then we use this. But specialized techniques automatically choose the order, variable order, as well as variable step size. So stiffness of ODs, I mentioned here, the step size h is decided by the largest absolute eigenvalue, and smallest eigenvalue decides up to which the ODs or set of ODs are to be integrated. So I'll come back to these statements. The stiffness is measured in terms of stiffness ratio, which is a ratio of absolute values of maximum real part of the eigenvalue to the minimum real part of the eigenvalue. And if this ratio is large, somewhere around 100, then it is said that the system is highly stiff. Okay. So just I'll come back to this. So how to choose the step size? So let's go through quickly. The selection of integration interval is very crucial parameter. So consider a linear ODE here. Dx by dt is equal to minus ax, and a is greater than 0. And analytical solution of this is exponential minus 18 to x0. And we define x star, that is true solution at Tn is equal to x star of n. And this true solution can be written in difference form, that is x star n is equal to exponential minus in place of t, I write nh, where h is a step size and n is iteration number. So n into h is nothing but t. And if I write for n plus 1, that is next iteration, next value, then it is minus a n plus 1 h and minus a n h and minus a h. So minus a n h is nothing but x star, that is your x star, and minus a h remains here. So this is difference form is written. Now consider the numerical solution of the same simple ODE, this ODE by Euler's explicit method. And it is xn plus 1 is equal to xn plus h f of xn. This is Euler formula. And the function here, the function is minus ax. So minus ax n at nth iteration. And this is nothing but 1 minus ah into xn. Xn is taken as common. So x, so after taking, the error due to numerical integration, that is approximate solution, is nothing but difference between the true solution and numerical solution. So as the number of iteration goes on, the error also having its own dynamics. So error can also be written in difference form. Error n plus 1 at n plus 1 is equal to exponential minus ah xn. So the true solution is written here, and xn, that is numerical solution, is written here. This one, okay, my 1 minus ah xn. So this xn is replaced by x star n minus en here, and then 1 minus ah is multiplied throughout, and we get the dynamics of error here, 1 minus ah en plus exponential minus ah minus 1 minus ah x star n. So error dynamics depends on the step size h here. Okay. So if I combine these two equations, the error dynamics and true solution, then we get this equations. Two equations are written in a compact form. Now, since a is greater than 0, original OD is asymptotically stable because we have minus exponential ah, and as number of iteration increases, x star tends to 0, right? So it is stable. Now, for numerical solution to be stable, the numerical approximation x star should have the qualitatively similar behavior as true solution. Means as the number of iteration increases, error should tends to 0. So in order to make sure this happens, the eigenvalue of this matrix, that is this matrix, should be less than 1. So eigenvalue of this matrix is given by this determinant lambda minus b, etc., equated to 0, and solve for lambda. And lambda is obtained here, that is absolute value 1 minus ah should be less than 1. That is so minus ah should be between minus 2 to 0. So this inequality constraint on h, this choice of integration interval h, step size, will make sure that the error vanishes as n tends to 0 as far as explicit Euler is concerned. So this condition is derived for explicit Euler method. Okay, explicit Euler. So say on a similar argument, we can derive the conditions for other methods like implicit Euler. We can see that for implicit Euler, the absolute value of 1 upon 1 plus h should be less than 1. So since this a is greater than 0, and for any value of h, if you choose, as far as implicit Euler is concerned, 1 upon 1 plus h is going to be less than 1. So we can say that implicit Euler is having better convergence properties compared to explicit. Explicit is having some limitation, but here any h you can choose. Similarly, trapezoidal rule, Simpson rule, is also having 1 plus h by 2 in the denominator. So h is always positive and better than explicit Euler characteristics. So for all the techniques, one can find out the suitable step size. So then, how to control the step size? So in these numerical solvers, some error is there when we compare it with true solution. And if we don't have the true solution, then the error is calculated as a comparison between the current approximation and the previous approximation. So suppose n is given, step size is given to us, and if we try to find out yn plus 1 from yn, then yn plus 1 can be obtained with the different step size. Suppose you take a single step hn, and you take two steps, that is you divide given step size into two, hn by 2. So in two steps we arrive at hn plus 1 if we divide by 2, and in one step we arrive at yn plus 1 if we use hn. Now if hn is small enough already, then this hn by 2 will be having a smaller step size. So if already hn is small, so these two estimate of n plus 1 obtained using hn and estimate of n plus 1 obtained by using hn by 2 in two steps will be almost identical. So the difference between yn plus 1 obtained using hn by 2 and obtained using hn, that difference is en, and if this is compared with the permissible error for all the variables en of I. So you have n variables, so for all the variables we find out the ratio of this difference divided by permissible error, and maximum absolute value is defined as q, and if this q is greater than 1, then whatever yn plus 1 we obtain is not acceptable because the maximum value is greater than 1. So it means that this error for the maximum value, maximum variable, maximum the ith variable is greater than the tolerance, not acceptable. So computation must be repeated with a much smaller step size. So now you need to repeat with hn by 4, and this halving of the step size is to be continued till q becomes less than 1, right? So the error parameter q, if it is less than 1 in the beginning itself, then in the next step we can increase the step size. From h to you can increase to 2h, etc., so that the computational load can be decreased. So after each step, q must be less than 1, else step size is to be reduced. So there are a number of criteria proposed in the literature. Some of the criteria I have mentioned here. hn plus 1 should be equal to hn previous step size multiplied by 1 by q to the power 1 by 4, or this. And this is how the step size is controlled during the iterations. So now let's try to solve multivariable problem using explicit Euler with this step size and initial conditions. And t is equal to 0, given t0, find out t equal to t 0.02. So this is actually the dy1 by dt and dy2 by dt with these equations. And the analytical solution of this problem is y1 is equal to 2 exponential minus 100t and 103 by 99 e to the power minus t, etc. And the eigenvalue of this matrix, okay, minus 1 and 100, minus 100. So this eigenvalue appears here. So y1 is changing very fast because exponential minus 100 times t, whereas y2, the change in y2 is dominated by this eigenvalue minus 1. Okay, so you can see that if I solve this with step size, then with a larger 0.2 step size, suppose, then the y1 is changing very fast, which we cannot observe here, and y2 is observable. So I have to reduce the step size, very small value. Then I will be able to observe the dynamics of y1. But for this step size, there is a very little change in y2. So step size h, okay, is decided by the largest eigenvalue. That is, in this case, minus 100 is the largest eigenvalue. That's why it is moving very fast. And smallest eigenvalue decides up to what time, okay, the ODEs are to be integrated. So in a small step size, in a for loop, you need to simulate this in order to observe the dynamics of all the variables. So this is a stiff problem. Okay, so CSTR problem also there. By the way, this is Euler, who had most of the techniques developed by him or based on his discovery. Okay, these are the MATLAB solvers available for ODEs, for stiff and non-stiff problems, okay, based on various methods. Okay. So I used to give this some interesting examples to the students. This is Belousov reactions. It's a classical example of non-equilibrium thermodynamics, which remain far from the equilibrium for a significant length of time and move chaotically. You can go through this web YouTube, and this is the dynamics of this problem. These three equations, semi-log graph, and I used to give this problem to my students to reproduce this figure using their own program. And another problem, interesting problem, is autocatalytic pathway. Okay. And you can see this y1 and y3 are changing slowly, but y2 increases very fast, then starts decreasing slowly. And a very interesting example is dynamics of A gives B gives C reaction. These are the three equations, and gamma are dimensionless parameters. You can see infinity value here. Gamma 2 is infinite, and gamma 5, two different values are given. So very small change in gamma 5 you can see, and for small change, different behavior is obtained here. So very interesting problem to reproduce this figure using MATLAB or your own program. Okay, so so far I have discussed initial value problem. Now I move to boundary value problem if time permits. Okay, okay. So so boundary value problems are those in which the dependent variable is specified at more than one value of the independent variable. And if it is in one dimension, then it is ODE BVP. And if it is in two-dimensional or three-dimensions, it becomes partial differential equations. Okay. So some examples from chemical engineering: heat conduction in metal bars, and diffusion cum reaction in porous catalyst. It is a Thiele problem or Thiele modulus, very well known in CRE. And tubular reactor with axial mixing problem. Fluid mechanics, that is velocity distribution in various geometries, Navier-Stokes equations are nothing but boundary value problems. So either we need to solve BVP ODE or BVP PDE. So three techniques, very simple basic techniques I'm going to discuss: finite difference, orthogonal collocation, and orthogonal collocation on finite element. So in finite difference method, this is known as a residual form function. So d square y by dx square dy by dx y x equal to 0. And with this boundary condition at x equal to 0, the boundary condition is to be, as it is a boundary value problem, two boundaries, some conditions are to be specified. Okay. So in finite difference method, the entire domain is has to be between 0 and 1. So if the actual dimension of x is x is independent variable. So if the actual dimension of x is, say, in centimeters or meters or millimeters, then it has to be normalized between 0 and 1. Okay. So assuming that already it is normalized between 0 and 1, so the domain is divided into n plus 1 grid points, equispaced, and xi is defined as I minus 1 delta x is equal to I minus 1 xn plus 1 minus xn by n, and I is from 1 to n plus 1, and the forward difference approximation, backward difference, and combining these two approximation of yi dash, we get yi plus 1 minus yi upon 2 delta x, which is usually used. And the second order differential is approximated by this algebraic equation. So the differential terms are transformed into algebraic equations by finite difference approximation. So this is the boundary value problem. So d square y by dx square is transformed by this approximation, dy by dx is transformed by this approximation, and boundary conditions can also be transformed into algebraic expression at ith grid point. Remember that we are interested to solve the problem only at grid points, not in the entire domain. So the residuals, these known as residuals, are forced to become 0 at internal grid points. So yi's are chosen such that residual becomes 0. And applying finite difference at boundary conditions. At boundary conditions, when we apply, we get some hypothetical points y0 and yn plus 2, which is outside of the domain. Y0 does not exist and yn plus 2 also does not exist. So these are the hypothetical points. And these hypothetical points are eliminated by boundary conditions. So let's quickly go through isothermal tubular reactor axial mixing problem. So it is 1 by 6 d square y by dx square minus dy by dx minus 2y square equal to 0. And with these boundary conditions, so y is a dimensionless reactant concentration and x is a dimensionless axial position. So let's assume that n is equal to 3, so n plus 1 equal to 4. So domain of x, that is axial position, is divided into 4 points, x0 to x1, and x1, x2, x3, x4 are the notations, and x1 is always 0, x4 is last, xn plus 1 is always 1 value, and corresponding y1, y2, y3, and y4. So we want to find out values of y at selected points. So point number 2 and 3 are internal grid points. So at internal grid points, these equation can be approximated. So here we need to approximate d square y by dx square and dy by dx by finite differences. So d square y by dx square at point number 2 and point number 3 are written, y3 minus 2y2, y1, etc. And the boundary conditions are also approximated by this dy by dx at x equal to 1 and 0. So it means that at the end of the reactor, there is no change in the concentration. And at the entry of the reactor, the rate of change of concentration is given by 6, 5, minus 1. So these boundary conditions are also approximated by finite differences. So now, y0 and y5 are hypothetical variables which can be eliminated by boundary condition, by writing the residual form at boundary points as well. So at point number 1, if you write the same equation, then y0 we obtained here, we obtained y5, and the from boundary conditions, y0 can be obtained in terms of y2, and y5 can be obtained in terms of y3. So wherever we have y0 and y5, they are replaced accordingly by using boundary conditions. So now 4 equations and 4 unknowns we have. Those 4 equations can be written in matrix form, and the nonlinear terms are collected on the right hand sides. This y square, y cube, etc. So it is in this form. This matrix, M matrix, is a constant matrix. Only the value of delta x is required. That is nothing but the different distance between the 2 points, and y vector and f phi. So this way the differential equations are transformed into algebraic equations, and now we need to solve algebraic equations only. The matrix M is a tridiagonal, you can see, with a constant coefficients. So Thomas algorithm can be so used. So if the right hand side is a linear, if this is linear, then it is a linear algebraic problem, then you can use any of this method. And if the right hand sides are non-linear, then you have to use Newton-Raphson or successive fixed point method. So it is in this form actually. This is m inverse f of y is equal to yk plus 1. So yk plus 1 is equal to m inverse f of yk. So at yk, at k equal to 1, the initial guess is given, so yk is available, and yk plus 1 is obtained as m inverse f of yk. And this iterations continues till we get convergence. So if it is a nonlinear, we use Newton-Raphson technique. That is, just now we discussed Newton-Raphson technique for multivariable problem. So yk plus 1 is equal to yk minus ak inverse of the Jacobian, and a function multiplication of the function value. So this function is nothing but 4 equations here that we have just obtained, 4 equations. And if you multiply on both sides with ak, that is a Jacobian at kth iteration, then it becomes ak into yk plus 1 is equal to ak yk minus f of yk. This ak inverse and ak cancel each other. And you can see that at k equal to 1, when we start with initial case on y vector, this ay multiplication is a number, it's a vector, and f is a function evaluation. So this difference is nothing but a constant vector fb. So basically it becomes a linear problem. So yk plus 1 is equal to ak inverse into b. That is what we need to solve. And whatever value yk plus 1 available becomes the initial case for the next iteration. So this is why this formulation is slightly different than the conventional NR method. So to form it as AY equal to B problem. So this is for n plus 1 general table. Okay. So in finite difference, we approximate the differentials with finite differences and transform differential equations to algebraic equations. Solve resulting algebraic equations by using appropriate method, which means if it is linear, then use linear methods. If it is non-linear, then use non-linear methods. And accuracy of the solution depends on the number of grid points. If you increase the number of grid points, then your accuracy will be more. You will have more information on the domain, but at the same time, the size of the matrix will increase and the computational load will increase. So we need to have some trade-off between the accuracy and the number of size of the problem. So can we continue? Raj?
Yes, sir. You can continue.
Thank you, thank you.
Yeah.
I hope all the participants are also okay.
No, we got the line, sir, and we are getting it somewhere.
Okay, thank you. Okay, I'll try to go through quickly. So next technique is orthogonal collocation, which is very popular for nonlinear problems, particularly because of its simplicity. So consider a simple, a general ODE boundary value problem, and here in the OC method, the solution of y as a function of x is assumed in terms of trial functions known as PIX. Okay. So yx is assumed as the solution of y, that is boundary value problem, is assumed as a linear combination of trial functions pi of x with some constant b1, b2, b3, etc. And it is truncated series. So in a compact form, it is written as summation of I is equal to 1 to n plus 2 pi minus 1 of x, where pi's are constants and it can be determined by using boundary conditions. And pix are the trial functions, set of trial functions. All these pi's, p0, p1, p2, etc., are linearly independent in the domain of 0 to 1. And they are mostly orthogonal functions. Orthogonal functions means the inner product is 0, that is p0, p1, inner product is 0, and dot product basically over the domain of x with respect to some weighting function. If they are not 0, then some weighting function is used. So in the presence of some weighted function, these trial functions become orthogonal. Why orthogonal functions are used? Because orthogonal functions can be the linear combination of orthogonal functions approximate nonlinearity very nicely. So some of the orthogonal functions are Bessel's, Hermite, Legendre, Chebyshev, etc. And these are the perpendicular vectors basically. So in OC method, the grid points need not require to be equispaced. You can have different delta x here. So if depending upon the nonlinearity of the behavior, this is your x domain and y is a dependent variable. So y varies highly in a nonlinear fashion as a function of x, then OC method will be better compared to finite difference, because if you use finite difference method and for highly nonlinear problem, then probably you may have to use more number of points so that you can capture the dynamics. But for more number of points, the size of the problem will become very large. So in orthogonal collocation method, with less number of points, with non-equispaced, you can have better approximation. So based on the Legendre function, which is defined by this, so pi and pj are orthogonal functions, that is trial functions, and with respect to wx, they become orthogonal to each other. And if we shift -1 to 0, that is 0 to 1, which is the domain of interest, okay, our domain of interest is 0 to 1 always. So it is known as shifted Legendre function. And if the wx, that is weighted function, is equal to 1, then it becomes 0 to 1 pix pjx, delta x is equal to delta ij. And for wx weighted function equal to 1, the pix are already obtained in the literature available, and the values of p0, p1, p2, etc. are given as a function of x. So if we insert these pi's in the solution, that is assumed solution p0, p1, etc., then what we get is this. And since b1 is a constant, and when you multiply b2 with this and b3 with this, so these pi's, they form another constants, and b2 when multiplied by the x again b3 with multiplied with x. So some coefficients of x, some coefficients of x square, etc. So it forms another set of constants. So yx is finally written as d1 plus d2x plus d3x square, etc. So this is the approximate solution of y of x for the boundary value problem, given this linear combination of trial functions. And since this is applicable at grid points only, we can write this yx for each point. That is y 0 to 1 is a domain of interest. And here, unlike the finite difference, the domain is divided into n plus 2 points. It's a convention. So y1 you can write for point number 1, for point number 2, point number 3 up to n plus 2 points. And so we have x1 and x2, x3, etc. So these are the set of equations, and this set of equations in compact form can be written as y1 to yn plus 1, yn plus 2, and d1 to dn plus 2, right? And this is the matrix known as Q matrix. Now, once you have this expression, this can be integrated as y dash x can be obtained. So differentiating once with respect to x, we get this expression, and for all the points you write this. So we get another expression y dash is equal to c into d. You can see the d vector is common between, but these matrices are different. And then one more differentiation, y double dash, we get this, and we get another compact expression, y double dash is equal to d into d. So in all these three equations, the d vector is common. So from the first equation, d vector can be obtained as q inverse y, and here I replace d with C into Q inverse into Y. C is a matrix, Q inverse is another matrix, so it is matrix A. Similarly for Y double dash, it is BY. So in nutshell, the first order differential is approximated by AY, second order differential is approximated by BY. Okay, so how to do this? What next? So what is, so let's go through this tubular reactor problem again. 1 by 6 y double dash minus y dash minus 2y square equal to 0 with these boundary conditions. So this y dash here is to be replaced by bij yj, and y dash is to be replaced by aij yj at ith grid point. So assume that n is equal to 2, so n plus 2 is equal to 4. So your domain is now having 4 points. However, the points are not equispaced, we can see. And how to choose delta x? And what are the matrices A and B? Okay, so these questions are there, which will be in a short while I'll answer this. So at internal collocation points, now here we call these points as internal collocation points. For point number 2 and point number 3, this equation can be approximated by an algebraic equation. Differentials are approximated here. So y double dash is replaced by j equal to 1 to 4, here n plus 2 is equal to 4, so j equal to 1 to 4, bij yj, and this y dash is replaced by this, and y2 yi for ith grid point. And since we are writing for internal points, for I is equal to 2 and 3, we have two equations. The boundary, here we don't have hypothetical points like finite difference. Okay, so boundary condition is also written in terms of approximation. So y dash is equal to 6y minus 1. So first boundary condition, since it is a first point, the domain y1, so it is j equal to 1, 2, 4, and it is a first order differential. Okay, dy by, so it is replaced by A matrix A, and it is a first point, so first row of A matrix is used here, and since this is the last point, fourth row of A matrix is to be used. That is n plus 1, right? So now we have four equations. The first boundary point a11, y1, a12, y2, etc. And right hand side is 6y minus 6. The second and third point, internal points, and last point. So now what are these matrices and what is the value of delta x? So for that, the matrices and delta x values or xi values are already tabulated in the literature for orthogonal OC method. So n plus 2 is equal to 4. So these are the values of x1, x2, x3, and x4. You can see the first and last value is always 0 and 1. And A and corresponding A and B matrices are given. Right? So we just need to pick up the value of Aij and Bij from these matrices and plug it into these four equations. So we end up with finally this matrix, and Now the right hand side, if it is linear, then you can use, so this can be formulated as yk plus 1 is equal to inverse of this matrix multiplied by f of yk. And initial case, if it is available, you can evaluate f of y this right hand side, and you can invert this matrix and you can get the next value of y. So basically here also the differential equations are transformed into algebraic equations by OC method, and resulting equations can, if it is linear, then use linear techniques. If it is nonlinear, then use nonlinear techniques. So this is about OC method. I am not going to show you the results of the simulation of this using finite difference, and it will take a little more time. I think I won't be able to cover the partial differential equations, but let me at least complete OCFE method, which I will keep it as a last topic. So now in OCFE, orthogonal collocation on finite element. So entire domain here is divided into several subdomains, and each subdomain is called finite elements. And in each finite element, on each finite element, orthogonal collocation method is applied, and number of internal points in each element can be chosen by the user, need not require to be same. So this 0 to 1 domain is divided into small finite elements known as H1, H2, etc. up to HNS. And since we are dividing the X domain into subdomains, domains of U1, so we need to H1, we need to define new variable, independent variable, that is U. So how it is defined, let's see. A new variable is defined, that is U, on the ith element, such that it is 0 at the beginning and unity at the end. So it means that the H1 is always 0 here, 1 here, H2 is 0 here, 1 here, likewise. So each element is 0 at the beginning and 1 at the end. So originally the entire domain was 0 to 1. Now each subdomain is also further normalized into 0 to 1. So how it is normalized? Let's see. So Ui is defined as x minus xj upon hi. So I is equal to 1 to ns, number of finite elements, and j is defined as 3 into I minus 1 plus 1. So if I put I is equal to 1 here, so I get j is equal to 1. So xj 1, so x1. And x1 is always 0. The beginning of the original domain is 0 always. So this is 0. So u1 is x by h1. And similarly, u2 is also, u2 is x minus x0 upon h2. So j is, I is equal to 2, so you get x4 here. Okay. So usually two internal collocation point in each finite element is usually sufficient. It is better to increase the number of finite elements than the number of internal collocation points. So if then in each finite element, orthogonal collocation method is used. So those tables can be used here. So example, same problem, tubular reactor with axial mixing problem, and assume that first element is having length h1 is equal to 0.3 and second element is having length 0.7, because original domain is 0 to 1. And and assume that there are two orthogonal collocation points in each finite element. Okay. So we have divided original domain into two finite elements, and in each finite element, two internal points. Okay. So 4 points in first element and 4 points in second element. However, total number of points are 7. The reason is that this point number 4 is common between first and second element. So now the first element is 0 to 1, that is U0, U1, 1, and second element is also 0. So U2 is 0 here, but U1 is 1, likewise. It is defined in that fashion, and so there are 7 points, and point number 4 is a common between two elements. So now first consider the first element, point number 1 to 4, that is H1. So this is to be replaced. The original problem is x is to be replaced by u. So we have defined here u1 is equal to x by h1. So x is equal to u1 h1. So h1 square is constant, and u1 square, d square y by du1 square minus h1 by h1. Okay. So at point number 2, this is the second order differential. It is to be replaced by Bij matrix. And since it is second point, second row of B matrix is used here. Second row of A matrix is used here. and y2. Similarly, the point number 3 is a third point in the domain. So third row of P matrix and third row of A matrix is used. So these two are the algebraic equations obtained for point number 2 and 3. Similarly, point number in the second element, that is point number 4 to 7, second element, uh, the internal points are point number 5 and 6. A similar fashion, now here we have 1 by s2 square. And since this is point number 5 is a second point. Point number 5 is the second point in the second element, the second row of B matrix, and the second row of E matrix, and point number 6 is the third point in the second element. So the first, two, second, third, and fourth. The second point and third point, actually point number 5 and 6 we are talking about, so which are the second and third point in the second element. So that's why second and third row respectively are used of the matrix. So now 4 internal points already algebraic equations are obtained, and point number 4 is a common between two elements. So shall we choose the first element or second element to include this point? So how to maintain the continuity between the two elements? So the solution should not become discontinued. So in order to maintain the continuity between the two elements, the slopes of u1 and u2, y at u1 and y at u2 at internal points number 4 must be same. So if you equate the slopes, then the continuity is maintained. So dy by dx at point number 4 for the first element, that is dy by dx is equal to 1 by h1, dy by du1, 1 by h1. Since it is the fourth point, it is the fourth point in the first element, it's fourth point, fourth row of A matrix is used, and the second element, the fourth point is the first point in the second element. So first row of A matrix is used, and this right hand sides are equated. So this equal to this term equal to this becomes the algebraic equation for point number 4. Then at the point number 1 and point number 0, that is first point and last point of the original domain, we have boundary conditions. So boundary condition for entry of the reactor is dy by dx is equal to 6y minus 1. So since it is the first point, first row of A matrix is used, and the second element, the last point, it is the last point, and dy by dx is given as 0, no change in the concentration at x equal to 1. So 1 by s2, it is a second domain, and fourth row of A matrix is used. So now all the equations are available, and writing all these equations in the algebraic equation form, we get this matrix for the same problem with the two elements here. If you increase the number of elements, then the size of the matrix will go on increase. And if it is a nonlinear problem like this, then the same way I explained can be used to find out the solution. If it is a linear, then you can use linear solution methods. So you can see that this matrix is a constant matrix. Okay, these are the numbers A, H1, etc. Okay, so this matrix can be taken on the right hand side, inverse of this matrix multiplied by this vector at initial. So yk plus 1 is equal to A inverse k f of yk is the solution, and you can continue iterations. Okay, so I think I stop here. I've taken a lot of time. Partial differential equations I could not cover, but this boundary value techniques, finite difference, finite element, and OCFE can be easily extended to partial differential equations also.
Yes, sir. Actually, thank you very much, and it was really interesting, and I also learned from here at least this orthogonal collocations because I never used it so far. So I'm thinking to use because it reduces the number of the equations, right, as compared to other methods.
Yes.
So any question from participant side they can ask actually.
So I did not include any research problem here because
No, this fine because techniques we
tech-
this course
techniques that,
as I
is,
told you this here we want to learn actually. So once we have learned the technique very well, we can apply
yes.
it anywhere actually.
In fact, this CFD softwares this fluent, etc. In the background of this, in fact, the advanced discretizations are used. I have not covered hierarchies and other methods, but in the background of these softwares, basically these techniques are used to solve the boundary value problems. In fact, in Aspen or Aspen High Seas also, the steady state flow sheet problem is solved by Newton-Raphson kind of code. Of course, more powerful code than what I have shown you, a very simple algorithm. But and the foundation of these packages, Aspen or CFD packages, are basically these techniques only.
Any question? Achal, do you have any question?
No, sir, it was a really good session. I really
Okay.
liked it. Yes, sir.
So, any question from other participants? They can ask actually. Sir, can you mean to suggest some book actually where people can go through it more detail maybe?
Yes, I will send you the slides, and I have not yet included the references. Okay,
Okay, okay.
so I will add some references, some textbook or some
I would think
reports.
that for orthogonal collocation actually, so you have shown that table you have 5 point somewhere.
Yes, yes, yes.
Those,
So original paper by Finlayson. Okay, that original paper I will send you.
Bruce
So,
E. Finlayson, right?
yes, yes. The,
Yeah, he has wrote one,
book
also
is,
one very short books, right? That
yeah,
introduction to
book is
chemical.
there. The one
So
original
no,
paper.
no, that book is very concise. He has covered entire chemical engineering nearly in 100 pages something.
Yeah.
A very short book actually.
So
And
I have his original paper on this orthogonal collocation method.
so my question is that those 5 points are sufficient to solve any equation?
No, no, no. These are the
Okay,
simple problems I have included, but for real problems, you really need to find out the optimum number of finite elements, and you have to trade off. There has to be a trade off between the number of elements and number of points and the accuracy and size of the matrix. In fact,
correct,
the
correct.
size of a matrix becomes very large. We have seen that it becomes more and more sparse matrix.
Right,
Okay,
right.
so its inverse becomes difficult sometimes. So more zeros, if you increase the number of points, number of elements, then more zeros will be there, and log
Right, right,
factorization.
right.
So inverse of such matrix becomes difficult, and so one has to have some trade-off between the size of the matrix and accuracy.
Yeah, people use to avoid this the inverse of matrix thing. People use some mass matrix concept also, right?
Mass matrix, it is in, I have in a differential algebraic problems, mass
Hmm.
matrix.
So, any questions from participants before we will close today's session actually?
Sir, my question is that how to remember such many numerical methods? In numerical methods, there are so many methods: Jacobians, differentiation, numerical integrations, Runge's method, Runge-Kuttas method. How to remember such big formulas?
So if you are a researcher, then you don't need to remember. You can always refer references. But if you are writing exam, then you have to remember.
Okay,
Even if,
okay.
sir, these days, let's say for smaller formulas, so most of the time, um, mm, people ask you to buy it, but some larger formula thing, something, and
See,
generally those are given actually. You should understand how to use and access.
see in a research course like MTech or PhD, when you do the coursework, then most of the exams are open book exams. So you don't need to remember. At undergraduate level, we don't keep such rigor. In most of the undergraduate course, most of the colleges are teaching only Rumble Kutta and order, not all the methods. So Runge-Kutta-Euler are a simple formula you can remember, and nonlinear algebra, Newton-Raphson are rarely taught at undergraduate level.
But even if you look formula wise, so if you are talking finite difference and also formula wise also they don't have anything big. Only thing they need some formulation, right?
Techniques you need to just remember and
Yeah,
formulation.
yeah.
So many formulas are there. Trapezoidal method, Simpson's rule. Many formulas are there.
Yes, it
Yeah.
is there, and we have to live with this formula.
So, any other questions from participants before we will close this session for today? So, if there are no more questions, I would say this is indeed a wonderful session actually, and I was actually looking for the time this should come for PD, but unfortunately, time
Yeah.
was not in our favor. So, hopefully, we will expand these techniques based on your slides. You will share to that PD part.
Yes, PD part also I will share.
Yeah. So with this, I would say because I contacted you in the last moment, you actually accepted this thing, and you were intended to have higher end questions, but I intended just to train the participants because if they have training, they can do the problems of high ends actually. So you have planned a lecture in such a way that everything was a wonderful way. It was nicely explained and nicely used in some examples also. And as far as with coding also, so everything is being covered actually in a very nice manner. So with this, I will say thank you very much once again to be the part of this short-term course. So thank you very much and thank you
I
for all participants.
thank you, Raj, for inviting and
So we will have in future we will have some exclusive talk maybe on PD because most of the time OD sometimes people manage people feel some difficulties in formulating the PDs actually
the
because
formulation
usually
is important. Once it is formulated, then it is
yeah.
easy to solve.
So in future we will plan maybe some other workshop especially
Sure.
on PD and some other techniques. So we would invite you in that particular course also. So with this, thank you very much, sir, and thank you very much for all these participants. So we will close this session here, and tomorrow we will assemble again at 10 o'clock. So first lecture tomorrow is development of DNS solver for incompressible flow using body fitted coordinate system by Professor Syed Fayed Anwar from Department of Mechanical Engineering, AMU. Next is formulation of governing equations and solving with finite difference in heat and fluid flow case by Professor Sachin, Department of the Mechanical Engineering, Imperial College, Pune. So these would be two sessions for the tomorrow from 10 o'clock onwards. So with this, we can end this session here. Thank you very much once again.
Thank you.
Yes.